Hey, welcome everybody, and welcome to a second semester during our pandemic where we're going to do our labs virtual. And let me begin by explaining that. So this is lab number 1. Last night I sent you out your assignments for this week. Which include reading chapter 15 and start working with 15. And today's lab, our first video lab, is really along those lines of chapter 15. So I will kind of give a general explanation here of how we're going to do these virtual labs first. But then as I roll into the lab here, I'm going to say, make sure you read chapter 15 first. It'll help, okay? So now that I've said it, you'll hear me say it again, but just want to know that if you haven't looked at chapter 15 yet, you should do that first before you do the lab. Okay, so let's talk about the lab. All right, so for some of you, this is the first time doing a virtual lab with me. You're new. You just came from Physics 121, and I haven't been your instructor. Although you might have had me for 102. No, probably not the way. No, probably not. So forget that. But others of you, you've had me already for 122, and for you guys, let me just say the virtual labs are going to run the same way as they did last semester. I kind of like the way it works. I think we've got some improvements that we could do, but in general, I think it worked well, and so I'm just going to do the same thing. And so let me explain that for those of you who are new. Here's how it's going to work. In a face-to-face setting, what you would do is you would come into the lab and you would get a lab partner, and you and your lab partner would work on them together. And there would be a bunch of lab partners, 15 groups to be exact. And so there'd be 15 groups of 2 people working with the equipment. So the way I'm going to do it in the remote setting is kind of along those lines, and it's going to pretend that I and you are lab partners, okay? So I will essentially be the hands of the lab. I will be the ones here with the equipment. And so for today, you can kind of see I've got some weights here. I've got a hanging spring up here. I've got a meter stick and a 2-meter stick. I've got a stopwatch, and I've got some masking tape, and I think that's all we're really going to need. If we need anything, just like in a regular face-to-face setting, I would say, oh, excuse me, I'm going to go run over to the cabinet, and I'm going to get it and come back and make our measurements. So I'm going to be the one in the lab, and you're going to be the one to write down the data, and hopefully between those 2, we will be like partners in here, and it would be just as close as we can make a virtual lab, as close as we can make a real face-to-face setting. And so hopefully with the video cameras and me kind of explaining, you'll get the idea of what you would have been doing had you actually been in the lab and put your hands on it. But then of course you will also then take that data, you will make graphs, you will draw conclusions, you will answer questions, and eventually you'll put all of that onto Canvas and upload it and submit it as your assignment. So today's lab is the simple harmonic motion one, and more on that in just a second here. But in general then, I will make one of these each week. I will send it out, and this is Monday already, and so hopefully I will get this out by Monday evening or even late afternoon to you. And you can do it whenever you want. If you read through my description that I sent out in the first week, you have all week to do the lab and the reading and the lecture, and so this lab is due on Sunday night. And so if you get this on Monday and you want to just pound it out and be done on Monday, great. If you would rather wait a couple days, depending on your schedule, or you really should do chapter 15 first. Now, not necessarily all the homework, but at least all the reading and the video watching first before you do this one. So you probably don't want to even mess with this one till Wednesday or Thursday. As I said in my intro, probably best to do at least a little bit, maybe most of it by Friday, because Friday I'll be available all day for Zooming and answering questions. And so if you have any questions, that would be a good time to just pop into the Zoom session and say, hey, I really didn't understand question number 2, or I was having trouble with this data, you know, whatever the case may be. Most of the time, at least based upon last semester, students who pop into the Zoom, it's more about the homework than it is about the lab, but, you know, anything, you know, goes. And so, anyways, and so just make sure you finish it up and upload it before Sunday night, midnight. That's the idea. And I'm hoping to actually do not only this lab, video lab this week, but also next week's video lab, so that I'm kind of ahead of the curve. So when I send out the week assignment next Sunday for week number 2, I will have connected with it lab number 2. So hopefully I can get 2 done this week and, like I said, be ahead. But we'll see how it goes. Meanwhile, let's just focus on this one. And so I will point out that here is the lab manual. Now, of course, I have it here in hard copy format. I sent it to you yesterday with that all those instructions to start the semester. And so it's down there in one of the many pieces I sent, but this lab manual you now have in PDF format, okay? And so to get started with today's lab, go ahead, and probably best to just download that PDF link I sent you and put it on your desktop or somewhere on your computer hard drive, excuse me, so that when I refer to this, you can, you know, have it, and you're going to need it each week. So once you've downloaded it, turn, and I'm going to have you turn to page 1, and here it says, simple harmonic motion. And now that you've already done chapter 15, you know that that is the whole idea of chapter 15, simple harmonic motion. And so we're going to actually test the theories and the equations that we've worked out in chapter 15, and actually some equations we worked out way back in chapter 7 in Physics 121. That'll actually be the first step, and then we'll get into the new stuff here, which will be steps 2, 3, and 4. So we're going to do a little bit of really Physics 121 first, and then 3 steps of our new stuff here, okay? And I'll let you go ahead and read that introduction here in chapter 1, and it's a lot like what you've read in the book. In fact, the introduction goes on to page 2 and then begins here. And it says, here is the procedure. And there's 4 steps. The 3 of them are on page 2, and the 4th one is on page 3. And so let's just do the lab together. I've got my yellow pad here. Let's see, I've only got a couple of sheets, so I was going to throw this top one away because I wrote on it, but I think I might need both sheets before the lab's over. So I'm going to try to conserve a little paper here and say I'm going to write down this data, and I'm going to, you know, hold it up and show it to you, because your job then is to go ahead and, you know, record down this data as I make the measurements, and so you are going to do some graphs. If memory serves me right, I think you have 2 graphs and a couple of calculations and 2 questions you have to answer. And again, that's what you're going to write down or type into your computer and then make into a PDF and upload into Canvas under the assignment. You'll just click under the assignment and it'll say file upload, okay? And so just write everything out. And you can do it the old school fashioned way where you just write everything out by hand, although the graphs really need to be done with a computer, and so I'll give you some options on how to do that with the computer. And then once you write it all out, again, if you do it on the computer, you can save everything in a PDF format. If you write it out by hand, which I think actually doing the homework that way, old-fashioned by hand, is best, then you can either scan it or use your phone to take a picture, which then use one of these apps that convert the pictures into a PDF, and you can upload that into Canvas. And if you can't make it into a PDF, I'll still take it. Just upload the JPEG of the picture. That's fine. But I will ask that try your best to turn everything into a PDF. Canvas is designed to work around PDFs, and they work much better on my end if I get a PDF. But if you can't make it a PDF, so what? Just put the picture up there, and then I'll deal with it. It's like I said, it's not really designed that way, so it's kind of a hassle when I get the pictures, because then I got to download them and put them on my computer, and then I've got to open an imaging software to look at them. And so again, that's why I prefer the PDF. So do everything you can to make it the PDF, but if you can't, just give me a picture, and I can work with that. All right, so let's start our first video lab. And I will begin with the theory, so I'm going to grab my marker here, and I guess I'll go on to the far side here of the board, and let's talk about step number 1. And like I said, step number 1 really takes us all the way back to Physics 121, and so for some of you that's just last semester, but for others of you, this is 2-3 semesters ago here. But it has to do with Hooke's law. So let me come over here. I'll put here step number 1. I'll even put here Hooke's law. And Hooke's law was introduced to you in chapter 7 of the, well, it doesn't matter if you did the Survey book or you did the OpenStax book. They both have chapter 7 where they introduce Hooke's law there. And Hooke's law basically says this, that if you have a spring, the force from a spring, so I'll call it F sub s, force from a spring, is equal to negative kx, where this k is what we call the spring constant. It might have a value of, say, 9 newtons per meter. Now, that's not to say every spring has a spring constant of 9 newtons per meter. I'm just making a number up. And that's roughly the number for the spring we are about to use. And so that's why I thought I would use it. But what that means then is if you have a spring, and maybe you hook that spring to the wall, and the spring has a natural length, and if you pull it from its natural length, that is, you stretch the spring, let's call that a distance x. And so the amount of force that spring is pulling back on you is equal to this spring constant times how much you pulled it, what distance you pulled it. And so the force from a spring gets bigger and bigger the more you stretch it. And that might even be obvious, but you don't have to have a physics class to have played with a spring and just know if I pull it a little bit, it pulls back a little bit. But if I pull it a lot, it pulls back a lot. And the more I stretch it, the harder it is to pull it. And it's a linear relationship, and so this is called Hooke's law. What's neat about this spring constant is it's really a conceptual number. And I get to use my fun phrase that I love the chance to use it. And so this is the first time this semester I get a chance to use it. Let's read the math a little bit. You know, what does 9 newtons per meter mean? Now, I mean, I can do the math. I could just, put a 9 and multiply it by the distance x and get a force. But what does 9 newtons per meter mean? And what it basically means is this spring, that if you stretched it a whole meter, it would pull back with a force of 9 newtons. Which, of course, means I get a force of 9 newtons for every meter I stretch it. So if I were to really stretch it, I don't know, my arms can't quite go 2 meters out, but if I were to stretch it 2 meters, then I would get a force of 18, because I get a force of 9 newtons for every 1 meter. That also means if I only stretched it a half a meter, I would only get a force of half of 9, which is 4.5 newtons. Because again, reading the math, the 9 newtons per meter means this is the amount of force I get for every meter. And if I stretch it less than a meter, I get less than this number. If I stretch it more than a meter, I get more than that number. But the 9 is what I get for every meter. And if I could stretch it, 3 meters, I would get 9, 9, 9. I would get 27 newtons. All right, but I'm not going to be stretching it that far. Now, the other little subtlety I want to remind you of from Physics 121 is x is measured from its natural length. That's important to realize, that x is not necessarily where you might want to put your grid. You might go, okay, I'll put my grid right at where the wall begins, and that's fine, but that's not the meaning of the x in here. So x is not your x-axis. X is how far did you pull it from its equilibrium. Now, to avoid any confusion, it's usually then best, unless there's other reasons going on in a problem, but it's usually best then to put your origin at the natural length of the spring so that the x of your axis and the x in this equation mean the same thing, and you don't get yourself confused. Again, that's why it's so important to make sure you're reading the math. What does that x mean? Because that x might be different than the x of your grid. And so you have an x for your grid, but you also have this x in this equation, and this x from the equation is measured from the natural length of the spring. Well, I probably said too much here at the beginning because this is all review. This is stuff you already did in Physics 121. And so, like I said, this step 1 is really just to test Hooke's law and also to find the spring constant. So here's what we're going to do in step number 1. In step number 1, we're going to collect some data. We're going to say, let's stretch the spring and measure it in meters, and then see how much force we get from that spring measured in newtons. Now, I left an extra space here because then to get this force, we are going to be measuring the force using weight and using gravity, and so we will actually measure the mass first and then use that to get the force. All right, so here's what I'm going to do here in a moment. I'm going to take a spring and I'm going to let it hang down, and that's going to be its starting point. That's going to be its natural length. That is what I will call x equal to 0. And so my first part of my table will be at 0 position. I will be hanging from the spring, 0 mass, which makes 0 force. But then I'm going to start putting on some masses here, and the first one will be 100 grams, which is 1/10 of a kilogram. So I will put 1/10 here, and the units are up here, 1/10 of a kilogram. And so we, as a lab partner, now I will be your hands, and so I will hook it up, and you need to write down how much it stretches. Then we need to figure out how much force that is. And so we will continue with more and more mass until we get to 500 grams, which is 1/2 kilogram, and stop. Okay, and so that will give us 6 pieces of data, 1, 2, 3, 4, 5, 6, that we can then put on a graph. And as we put them on the graph, we will plot the force of the spring here, and we'll just do absolute value, so we won't worry about the negative sign from Hooke's law. and then we will have the X, and then we will put in our values. And hopefully we will get something that looks 1, 2, 3, 4, 5, 6 linear, because that is what Hooke's law says. And of course, the slope of this thing would be that factor right there, the spring constant. I'm thinking of this in terms of, okay, this is what I'm plotting on the x-axis. This is what I'm plotting on the y-axis. So this out here would then be the slope. And so I can then take my data and measure the slope and find out what the spring constant is. All right, let me actually come back over here to the equipment, but I'll actually read the part that it says here. So it says right here in the procedure, part 1, it says, determine the spring constant of your spring by measuring its extension for various loads. Okay? And so that's what step 1 is all about. So let me come around to the front of my table. And here is the spring that I was mentioning. It's already hooked up and kind of ready to go here. Let me make a little data table so that you can see it a little better on the video here. But for step number 1, like that table up there, I'm going to have an X. How far did it stretch? Okay. In units of meters. I'm going to put in the mass in units of kilograms. And then I'm going to get my calculator, which actually maybe I'll just do it on the graph. And instead of go grab a calculator, but then I will measure the amount of force on the spring in newtons. And as I said, we will go 0, 0.1, 0.2, 0.3, 0.4, and 0.5. And so there will be our 6 pieces of data. And the easiest one first is, of course, the putting no mass. That means it's stretched 0. That's its natural length. And, of course, 0 mass times force. And so I'll just use mg again, going back to, I guess this would be chapter 5 of your 121. You know, what's the connection between the mass and the force, the mass and the weight of an object? It's mg. All right, so I told you this was kind of a review in this first one, coming back to the physics 121 stuff. All right, so now let's look at our equipment here, and to make this work well, I got to do a little setup here. Let me grab a little bit of masking tape here. You'll kind of see why here. I've got my longer 2-meter stick and a shorter 1-meter stick. And if I just put the 2-meter stick up against the spring, and then take the 1-meter stick, and as carefully as I can, tape the 0 of the 1-meter stick against my 2-meter stick. And so now the 0 on this 1-meter stick is measuring the natural length of this spring. And so as it stretches down, I can just read it off this 1-meter stick. All right, now I'm going to have to make a rough guess that I'm going to put a piece of tape where I hope I don't have to take a reading from. So just to hold the meter stick in place, I'm going to put it down here. Oh, by the way, I did the same thing on the top one, but I know from experience that it stretches more than that. So I know that tape up at the top is not in the way. I just hope this bottom one is not in the way. And so usually what I do is I get a second one ready. And in the unlikely scenario, that I need to make a reading right where this is. Actually, I can see through it pretty good, so maybe I won't even mess with it, but I can put a second one right here and then undo that one, but it doesn't even look like I'll need to do that. This tape's pretty transparent. All right, so here we go. Let's get our first set of data. And so I'm going to grab 100 grams here and hook it up. And hopefully you can see it's stretched down. And now, of course, the force pulling up from the spring is equal to the weight of the object. In fact, this math I can even do in my head. This would be 0.1 times 9.8. So that force would be 0.98 newtons. And so there's the force. And, of course, now I would want to know where the bottom of that spring is, and I am probably around, and sadly the spring kind of coils like this, so it's not level all the way down. So there's going to be some imperfections here, so I'll keep in mind that it won't be perfect. There's other reasons for imperfections also. But maybe I should call that 12.0 centimeters. And of course, I'm going to record that in meters. So I'm going to put a 0.120 for the distance. So that's how much it stretched. So let me swap the 100 out for a 200 and hook up then the 200 and see how far that went. Okay. So again, kind of coils there, but I guess I'm going to just take this mark as it keeps coiling more and more. So why don't I just call that a 15.1? And so 15.1. Let's go to 300. These brass weights are nice. They've got a little, oh, this one's kind of jammed up, but I can still reach it. There's a little hook underneath. And so the 200 with the 100 make the 300. And so how far does it stretch now? Okay. Wasn't that a 25 one? I'm going to come back to that one. I think I wrote that one down wrong. I apologize here, but let me get the 300 why I'm here. Okay, so let's go to, let's call it 37.8. So 37.8. And I'm going to go back to the 200 because I think I messed that one up for you already. Because I think it was a 25.1 is what I wanted. Yeah. Okay. So let me fix that here. All right. So this is a 25.1. Okay. All right, so that's the 300. Let's go to 400, and I have two 200s for that. So let me take the two 200s here, and I'll take it down. Oops. And kind of look here. But why don't we call that a 50.5? And so 0.505 for the 400. And then the last one here is to put the 100 on. All right, so I have the 200, and the 100. So there is a total of 500. And if I kind of use this corner again, let's call it a 63.3. And there's my data. Now, as we get a little further along, I will normally just kind of leave this alone and say, hey, you do the rest of this, you make a graph. But given that it's our first one, let's talk a little bit about this graph. So come on over here to the board with me here, and I'm going to take this data, and I'm going to actually remove this spring for a second so you can kind of see things here a little better. I need to come back to it, so I'm gonna, well, maybe I'll take it all the way down, but we're gonna come back to this as we get to step 2, 3, and 4. But I want to turn on the computer for a moment, because all of our experiments require you then to take some data and make a graph, okay? And I'm going to give you that option. You can do the graphs however you want. You can use any program you want. As I was saying earlier, the big goal is to really make a graph so you can turn it in, but then let the the computer calculate the slope, and then use that slope to draw a conclusion. And so for this first step, that conclusion would be, what is the spring constant? All right, so let me turn on our digital display, because some of you are already familiar with Excel spreadsheets, and you can just put it into Excel spreadsheet and do a graph. Others of you are familiar with Google Sheets. There's many other programs that can give you the slope, and so you can use whichever program you want, all right? But the one that I'm going to provide for you is called graphical analysis. And I would say the same thing if we were face-to-face. We've got the computers, and you can log on, and you can either use what I'm going to show you, graphical analysis, which is a very simple graphing program, or you can use your more sophisticated ones, kind of your choice. All right, but like I said, the one I'm going to show you is actually provided here by the school and by our program here. Now, what I can't show you, and so I'm going to send out a separate video when I get home, is how you would get to your student desktop from off campus. And I'm on campus right now. So when I start the computer, this is what my desktop looks like. It's the VM, the virtual machine. You should have gotten an email from our IT support as you started this semester that says, hey, how do I get to this campus virtual machine? Because when you do that, you have, because you're enrolled at City College, you have a virtual desktop, and you can use programs like Microsoft Word, Microsoft Excel, and one of the ones that should be on your desktop, because you're enrolled in my class, should be graphical analysis. And so that's what I'm going to show you, is from graphical analysis. And so like I said, when I get home, I will make a video of me at home using a remote computer to log into the virtual machine. I'll also send you the information that you should have already got from our IT team, but you may not have, which will show you how to download the virtual machine and how to install it on your computer so you can actually get to graphical analysis. Now, of course, those of you who already had me, you did this last semester, so you're good with that. But for those of you who are new with me this semester, I don't think Doug in 121 was doing the graphical analysis and maybe didn't use the virtual machine here. So like I said, I need to show you that, but I can't do it here from campus. So let me start here. Let me start from the desktop. And of course, your desktop, a student's desktop, will look different than my desktop. This is an instructor's desktop, and it also has some individual files that I normally use when I'm in a class setting. So let me emphasize, your desktop won't look quite like this, but here's what it will look like. This one right here will be on your desktop. Or if it's not on your desktop, you can go down to the Windows icon and go through all the programs until you get to the one that says graphical analysis, okay? So that's what you're going to need to do, because you need to take this data that I just recorded right here, okay? And you need to put it in here so you can get this first graph. This is the first step of our 4 steps for today's lab. And I'll say it again, in a normal setting, once we get rolling here, I'm just going to hold this up and say, okay, you take it from here. We're partners here. I did my part. I hooked up the spring and I got the data. Now you do your part. But for today, let me help you a little bit more by saying, let's look at this. All right, so what I'm going to do is I'm going to click on the icon here that says graphical analysis, and it'll start the program. And for those of you who haven't used graphical analysis, let me show you a quick couple of steps here. It is very, very user-friendly. So if you just start poking around on it, you'll get the hang of it right away. Watch this. You see by default, it has given me 2 columns and a graph. And graphical analysis is very simple because it just wants to do a graph. That's why it's so simple. And anything you want to change or adjust, you usually can just put your mouse on it and click on it or double click on it and make some adjustments. So the first one by default says X. Okay? So it defaults to X and Y. For our lab, I really want X and M for mass. So let me illustrate by moving my mouse to the Y-axis. I'll just put it right on where it says Y and double click. And when I double click, I get this dialog box that already has a Y in it, and then there's some other things I can put, and so I'm going to put right here under the name that is Y, I'm just going to change it to well, maybe I'll spell it out, mass, because the second little box says what's the short name or the symbol for it. That's where I'll put the M. And the next little box, I'll click in it for a second, says, well, what units do you use? And so, as I mentioned earlier, let's use kilograms here. So I'll put kg for kilograms. And then I'll just click done, and then sure enough, there it is. It says mass and the units are kilograms. Now I need to go back to the first column. The first column has X, but it doesn't have the units in meters up there. So I want to make sure I include those. So let me come over here and put my mouse right on top of the X. Let me double click. And of course, the default of X is fine. The short name is fine. I'll just put in an M for the meter for the units and click done. And so you can begin to see it's pretty user-friendly. You just put your mouse on what you want to change or adjust, and you double click. And once you start putting in data, it's gonna make that graph. Okay. Now let me just type in these values here. Okay, so if I put my mouse right on the first column X, there it is, the first cell, I can put a 0 and just arrow down or hit enter. I can put in a 0.12 and arrow down. I can put in a 0.215 and arrow down. I can put in a 0.378 and arrow down. I can put in a 0.505, arrow down, and I can put in a 0.633, arrow down, over, and all the way up. So I've entered the data.
Second value, was that 0.251 or 2.21?
Second value was 0.120.
No, maybe it's the third one then.
Third one should be 0.251.
Okay.
Okay. Okay. Yeah, so I hope that's good. And then the values, but thank you, Ron. Keep me from not making a mistake, because I'll really mess up the students if I make a mistake here. All right. So then this next column is the mass I was hanging here. Okay, and I'll say it again. Normally I won't go through this much detail on a graph, but this first one I want to. This first one I want to, kind of get you rolling. And if you don't want to use graphical analysis and you want to use Excel, that's fine. But I'm going to recommend graphical analysis, and that's why I want to show you A, how to use it, and then B, show you how to get to it from a remote setting. But like I said, I got to do that separate. I can't do that while I'm here on campus. Okay, so mass then would be, 0 in the first one, so I'll hit 0 down, then I'll hit 0.1, 0.2, 0.3, 0.4, 0.5. All right, and so there's my data. Now, you can even see that the computer is starting to graph this. Now, it's not graphing what I want. It has a default that it would plot the first column along here and the second column along the vertical axis, and that's not quite what I want, but it's a good guess by the computer. So I'll fix it soon, okay? But nonetheless here, I want X on the X-axis, so that much is good. But what I want is force on the vertical axis, and I don't even have that. So I'm going to take this as an opportunity to show you, well, then how do I get more columns? Because again, by default, graphical analysis just starts with 2, because it knows you're going to make a graph. You got to have 2 for a graph, but you may want 3 or 4 or 5 or 6. And so to get a new column, you're going to do this. Up here in the window where it says data, there will be one that says data new column. So sure enough, I'll come up here where it says data, and I'll just scroll down to new column. Now I'll pause here because under this category of new column, there is 2 options. There is a new manual column or a new calculated column. Now the difference between those is a manual column would just give me a new column and I could then type it in. So I would at that point have to get out my calculator and then calculate these by hand, that's fine, and then enter them manually. And that's fine if you wanted to go that approach. But since a computer is also a calculator, you can make a calculated column and then just put in the formula. And so the computer would do the calculations and make a new column. So for this particular problem, that would make more sense than to me to get out my calculator and do all these and write them down, only then to type them in. I might as well do that in one shot. So I am going to use the one that says a new calculated column. Okay, so new calculated column, and then of course I get a dialog box. And so it says, okay, well, what do you want to call this? And so I guess I want to call this force. And so there's force. What symbol do you want to use? Well, traditional symbol for the force from a spring is the capital F. So maybe subscript S, but I won't mess with a subscript. The units, as we mentioned earlier, would be in newtons. So I'll put a capital N for newtons under the units. And then, of course, the formula. And by the way, if I had done a manual column, this box wouldn't be here. It wouldn't ask for an equation. I would just hit done and it would make the column and I can then type it in. But for this one, because I said a calculated one, it wants to know not only what to call it, but then, okay, what is the equation? And so this is just mg. So it's the mass times 9.8. All right. So under this button right there that says variables, that is the columns, you can use any of the columns that you've already entered at this point as part of your formula, part of your equation. And so one of those is the mass. So I'm going to just come over here and select mass. Now I could have just typed in mass, but you do have to know the syntax, and so there's a double quote on each side. So for those of you who would rather type things out than to use a GUI interface, fine. I'm going to recommend the GUI interfaces. To type on a keyboard, you have to remember all the syntaxes. And if you're doing the same process a lot, yes, typing things out is much quicker. You become a good typist and you know all the syntax. But if you don't do something on a regular basis, the GUI interface is much easier. So that's what we're going to do, because we're going to do a graph. I think we got 2 or 3 today, but you know, not every week will we do a graph. Anyways, but that would be the syntax. And then the times is the traditional star symbol, you know, the shift 8. So I'm going to go shift 8. So there's the little time symbol, the little asterisk. And then, of course, times G, which is just 9.8. So I'll just type in the number 9.8. And so this is a simple formula for this one. And now I can just hit done. And watch what happens. So I'll hit done. And it made a 3rd column. It may not look like it because it scrolled over and you don't see the first column. And so you can see both of them. I'm going to go ahead and grab the window here and kind of stretch the window over my graph a little bit. In fact, actually, maybe I'll just pull my graph back so that I can see my whole table. But some tables get really big, so you don't usually want to see your whole table. Usually just 2 columns at a time is good. So that's how it defaults. But this one, there's only 3, and I still have a good size for my graph. Anyway, so there is the data. And like I'll say it again, this is what you need to be doing because this is what you are going to be turning in. You are going to be turning in this graph. And then, of course, you're going to write on this graph what is the spring constant. And so what is the slope here. Now, I'm not quite done with the graph because what I want to graph, remember, is to graph the force versus the position. And of course, the default, there's position, but it's mass, it's not the new column. So I got to make one small change here, and that is to come over here and click on this word mass. Remember I said if you wanted to change anything, just click on it, and you can see that all your columns pop up, and I can just select force. I could also go down to more, and then they would have check boxes. And in fact, that's the only way if you want to get more than one plot on the same graph you have to do, so you can do multiple checks. And so maybe I will uncheck mass and check force. And so there are my 6 pieces of data. 1, 2, 3, 4, 5, 6. Now, it's not taking up the whole graph, and hopefully you've learned, if not, I'm going to say it now, that you should always make a graph to cover your whole graph paper so you can see it. If you're not using the whole graph paper, you're just wasted space, and your graph could be too small. I call this, like in diagram, if I can cover it with my thumb, it's too small. It's way too small if I can cover it with my thumb. And most of the time, if I can cover it with my hand, it's still too small. So the Young test here, the Professor Young test of graph size is, if I put my hand on it and I can't see it, it's too small. All right, so let's change the formatting here. Okay, now, fortunately, computers have made our lives, well, both easier and harder, but easier in this case because there is a nice little button here. This capital A up here is the auto scale, and take advantage of that. You can scale it manually if you want, but the auto scale lets the computer kind of look at your numbers and expand the data, and oftentimes it does exactly what you would have done. Sometimes you want to go back and fix it, but at least start there. And so I think this auto scale will probably work pretty well. So I'm going to come over here and see what it gives me. And so I'm going to click on the capital A, auto scale, and then take a look. And it looks like on the vertical axis it gave me 0 to 5, and that's just below the top one. That's perfect. In the horizontal distance it gave me 0 to 0.7. It didn't label them well. I don't necessarily like the way it labels, but other than that, 0.7 is good because my last one's just beyond 0.6. So I'd say it did a good job. Really good job here. And sure enough, there's my graph. So again, this is going to be the first of your pages that you're going to turn in for your first lab here this week. Okay, so you need to do this one. Okay, now I'm not done. Yeah. So I'm getting ahead of myself here, but we need to get that slope in here. And so one last thing to show you here is how you do a curve fit. And this is the easiest of the curve fits because it's a straight line. And we have a couple of options. Let me show you the more general option first. The more general option is you just come over here under Analyze. And you come down here and you say, I want to curve fit it. And then you get a choice of, well, what kind of function do you want to curve fit it to? And you can pick linear, or in this case actually proportional, because since this is actually a proportional graph, not a linear graph. But that's one option. And I want to show you that one first because that's the more general one. But as you get more acquainted with this program and the simple ones that are a straight line, they've put an accelerated button on here, and you can see it right there, that little R for regression line. And so I'll just come over here and show you that one too. That's kind of nice. Just hit regression line. Boom. And the computer goes in and gives you a nice straight line, and then you can ask yourself, does my data represent a straight line? And I'd say, yeah. It looks actually really good. In fact, I would say that it looks like I kind of messed up on my first one right here. That 0.12 is a little bit off of the pattern from the other 4, or 5, counting the first one. But it's also very close. So I don't think I need to go back and remeasure that one. That one is, within reason. And so we know that as a human, we always make mistakes. Well, you wouldn't make mistakes, but your lab partner would. So, okay. So I know you're not going to make any mistakes. But given that we have to work together, your lab partner may make a mistake here and there. And so never is our data perfect. We understand that. And so we have these things called plus and minuses, right? We say, well, this is the value plus or minus something. Okay, and then so that's what we have here. And so if we come over here and look at this, and we look at the slope, it has measured the slope for us. And it says the slope is 7.7 newtons per meter. And that's perfect. And so what I want you to do is to turn in this first step. And there's going to be a lot more before the lab's done, okay? But for this first step, I want you to turn in A, this graph, and then B, I want you to write somewhere what the spring constant is. Now, you're going to say, well, the spring constant is just the slope. Yeah, well, it is in this case, but that's not always true. The slope is a value, and the slope leads us to something of value. So there is a difference between the slope and the valuable thing we're trying to measure, which is the spring constant. Now, in this case, they're one and the same. But I want you to write down, and you can either print this out with a hard copy and write it right on it and then scan it and make it a PDF, or save that as a PDF and then just take another piece of paper. You could just type it in a Microsoft Word, but I want you to say that the spring constant is, and in my case, I would write 7.7 newtons meter. And I know at this point you're thinking in your head, well, that's the same as the slope, and the slope's already on there. And I just want to emphasize, yes, I know that, okay? But I want you to be telling me that you know that the slope is the spring constant. So we have to go from something mathematical, a slope, to something, what does that mean, a spring constant? You'll see that in the next graph. You'll see that in the next graph we'll get the slope, but the slope will not be the spring constant. But we can use the slope to figure out what the spring constant is. So that's why I'm emphasizing I need to see both. I need to see a graph that says this is the slope, but I need you to write somewhere on here that the spring constant is 7.7. Okay, that you've made that connection. Okay, and so that's the idea here. All right, now. And by the way, if I don't see that, I'll probably just shoot you back an email and say, hey, look, I want to give you 100% on this lab. I want to give everybody 100% on this lab, and you didn't write that down, so hey, why don't you redo that and resubmit it? Because I want you to get 100%. And so that's how the labs work. So make sure you do all the steps in the lab, because I want everyone to get 100% on all the labs. That helps. That's 15% of your grade. So it's really nice to get 100% on 15% of your grade. Okay, so I guess I'd say I'm kind of done here. Let me power down my overhead with this first graph, and then let's go on to step number 2. And like I said, I hope I didn't take too long. I don't think that they'll always take this long, but I did want to have to make sure I did a little introduction to, okay, how are we going to do these video labs in this weird remote setting? It's just so different. And half of you are coming from Physics 121, and I don't think Doug was doing the labs quite the same way, and so you got to kind of learn me and how my class works. Now the other half of you know how it works, because you learned that last semester in 120, 122. But let me just take this as an invite that, hey, you ever have any question, shoot me off an email. I'm always connected. I know even when I'm not at home, I got my phone with me, and I can be standing in line at Vaughn's and answering student questions. I do that a lot here. So, it could be 3 in the morning and I'm watching a late night show and like, hey, send me an email. And I'll respond back. Okay, so I respond a lot. Weekends, almost anytime, and so you'll probably get an email right away here. Okay, so let me just put this up and say, okay, let's move on to something new, something related to this semester, and that's where steps 2, 3, and 4 come into play here. All right, so let me put step number 2. And step number 2, this is the part that I was saying at the beginning of this lab that you would be better off to have gone through chapter 15 already. I'll kind of highlight what we did in the lecture. We did something like this in the lecture. We said, okay, let's take some kind of solid fixture up above and hook our spring to it. So here is our spring hanging down, and so that will be the spring at its natural length. And I'll come back here and hook this one up again. And then if we come along and we hook up a mass M, it will extend the spring some distance. Let me call it x naught. And as you see in a moment, when I actually do this, I'll kind of hook it up and let it extend down and just let it rest right there. And so that's going to be important. This is at equilibrium here. Because then after I do that, I'm going to take one more step, and I'm going to take this mass and pull it down a little bit more. So let me draw a new picture. And so here is the mass M, and I have pulled it down a little bit more. Let's call it X1. Why not? So I've got a 0 and then I got a 1. And then I'm going to let it go. And so the question is, what happens? And let's just run through this math kind of quickly, because we did this in the lecture part. But it would look something like this. Okay, going back to Physics 121 and what we call Newton's second law of translational motion. It says if you add up all the forces, that has to equal to mass times the acceleration. So Newton's second law of motion. This you'll hopefully recognize from chapter 5 and 6 in your Physics 121. Okay, so if I look at the forces on this, One of the force is the force of gravity. So there's a minus mg. So gravity's pulling it down. But also the spring is pulling it up. And so this would be a minus k. Now let me come back to step one. Remember Hooke's law. The minus k, the x is how far the spring has been stretched from its natural length. So it is actually stretched the sum of these two x's. And so this is an x naught, and then this is an x1. That's the total distance the spring has stretched. And that would have to equal to ma. Okay, now, just for clarity, let me be a little careful here. I think when people see this negative sign, their first reaction is, hey, the force is negative. But remember, these are going down, so these are negative x values. So these are really negative with a negative, and so the spring is a positive force. So the spring's going up, and gravity is going down, okay? And so that's, in fact, that's what I want to get to. Without the x1, that should have been balanced and have a total of 0, because watch this. This is the neat thing about the vertical spring. Is that once you multiply this out and you look at these first two terms, remember this first distance, x naught, is how far did the spring stretch before it came back into equilibrium. And equilibrium, again, this is going back to Physics 121, this is chapter 12, equilibrium means the sum of all the forces is 0. And so right here, when I had pulled this down, or excuse me, not pulled it down, when I just hooked it on and then let it go so it wasn't moving, then this right here, the force of gravity, this one, is exactly balanced by the force from the spring when it is stretched a distance of x naught. So that is a nice way of saying that these two terms come out to be 0. And so what looked like was going to be a long equation actually reduces down to something a little simpler. And in fact, if we just had the spring horizontally, we wouldn't have had this force of gravity, and we would have just said the force is kx. And that's essentially what we have. So the beauty that I hope got across to you in the lecture part is that the equation for a vertical spring, even though there's a force of gravity, is actually the same equation as a horizontal spring where you don't have to worry about gravity. Now there is a difference though, and here's that difference. The difference is the x for a vertical spring is not measured from the natural length of the spring. The x on a vertical spring is then measured from the equilibrium. And so if you're willing to do that, if you're willing to call this x1, not the x from the natural length, but the x from the equilibrium, then this equation that you get for the vertical spring is the same as the horizontal spring. And so everything we learned about the horizontal spring, which was easier to solve than the vertical one, is exactly the same. And I probably said too much because I did that in the lecture. And I don't want the lab to go too long here, but I thought it might be good that you see it. Which is why then in my next step, I'm just going to go minus kx equals ma and not even have the 1 here, but emphasize to you that this x would be from equilibrium if we're dealing with a vertical spring, and that's what we're doing here in the lab today. And it would be its natural length if we were dealing with a horizontal spring, which we do a lot in the homework problems, but not here today in the lab. In fact, let me go one step further even and move the m over here to the left-hand side of the equation. And then let me also rewrite a as the second derivative of position with respect to time. And we get this beautiful equation. Now again, let me not take as much time as I did in the lecture, but this equation should look familiar to you if you've already gone through chapter 15. And so let me say it again. Here's the whole point of chapter 15. The whole point of chapter 15 is that if you take your Physics 121, you write out all your forces or all your torques, depending on the type of problem. If it's a rotational problem, it would be torques. If it's a translational problem, then it would be forces. But if you ever end up with an equation like this, as we talked about in the lecture then, the solution to it, what function can you take its derivative twice and end up with that function, is a sine or a cosine. And so we'll just put a phase shift in here, because a phase shift can turn a cosine into a sine. So this is really giving us both options. There would be some amplitude. And in this case, the amplitude would be however far I pulled it down. And this thing out in front, or at least the square root of that out in front, is what would go in there. And again, let me not take that extra time here in the lab. I've already probably taken more than I should have, but I thought it would be a nice little review. And I'll let you test it. If you go ahead and take the derivative of this twice, you will see that it does equal to that. And it's taking the derivative twice because of the chain rule that pulls this out twice, which is why this right here would have to be the square of whatever is right here. And so this little thing right here is what we call the omega. And of course we call that the omega because you can even see then, since you know that a trig function repeats itself every 2 pi, if we call capital T the period, that is the time for one cycle, then omega times capital T would be 2 pi. See, that's from our math class, we know when a trig function repeats itself. It repeats itself every 2 pi. So that means the period would be 2 pi over omega. That's why then, if we look at an equation like this, we can just simply look at it. We don't have to really solve anything. We can just jump over here and say, hey, I know what omega is. Omega is the square root of that stuff out in front. So not counting the x and not counting the omega, not counting the negative sign and not counting the x, the omega is the square root of that thing. So this would be 2 pi over the square root of k over m. Or to simplify it, it would be 2 pi times the square root of m over k. Now, of course, in class, we did a lot more with this. We not only got its position, we took its derivative to get its velocity, we took the derivative of that to get its acceleration, we multiplied by mass to get its force, we've got the period, we could take the reciprocal of that to get its frequency. And what I said in the lecture and want to just kind of repeat now is once you get to this equation, you're done. You know everything. Okay? And so the real key of this chapter is to start off with Newton's second law, either of translational motion or rotational, because, you know, we could have the harder physical pendulum ones where we got to do torques. But this is just a simple straight up and down, so this is a translational problem. And if I write it out and I ever end up with an equation like this, once I know this omega, I know everything about this problem. I know the equation for its position, I know the equation for its velocity, I know the equation for its acceleration, I know the equation for the force, I know the kinetic energy, I know the potential energy, I know the period, I know the frequency, I know everything. So I'll say it again. You want to get all your problems in this form, okay? Because that gives away what the omega is. Now for today's lab then, and like I said, maybe I did a little too much reviewing getting to this point, is let's use this equation. So I wanted to rederive this equation as well as just, you know, show you or remind you that you'll see it in your textbook. And of course I did it in class. And so what we are asked to do is now to use this same spring that we did in part 1 in part 2 here and make a little table and a graph that looks something like this. So what we're going to do is we're going to collect data for different masses, and we'll measure our mass in kilograms. And we'll see what the period is. Okay. Oh, and I'm right at the pole, Ron says here. Just inside? Oh, okay. So I won't go further than this. The pole's in the way. Now, I left an open spot here because to get some more accurate data, what I'm going to do is not measure one period, but to measure 10 periods, and then we'll take that number and divide by 10 in order to get 1 period, okay? And so I will start off by saying, all right, let's put in 1/10, 2/10, 3/10, 4/10, and 5/10. Okay? And then let's actually measure our period. And then let's see if it follows this equation. And then let's see if we can use it to get the spring constant. In fact, hopefully that sounds a little bit like we did back here in step 1. See, in step 1, we collected some data. We confirmed that the data followed Hooke's law, and we used that data to find the spring constant. So we're essentially going to do the same thing, but we're going to do it with what I'll call a dynamic measurement. We're going to having the motion going on, and it's more related to what we're learning here than what we did last semester. So this step 1 was last semester, or back in Physics 121, which could have been 2 or 3 semesters ago, and then this one right here. All right, so let's collect some data. So let me come over here to the front again here. Let me grab my data table here. Let me put table number 2 right here. Let me make a kind of a little chart like that so you can see it. I'll put mass in kilograms. I'll put 10 oscillations and record the period in seconds. And then we'll divide that by 10 to get 1 period, and that's how we'll collect our data. So as I was saying, we're going to be lab partners here together. Okay, so I'll do the hands-on stuff. You get the data, you're going to make another graph. And I won't go nearly as much detail with the graph this time. I'm going to leave that up to you. Okay, so let me just put point 1, a point 2, a point 3, a point 4, and a point 5. And let me set it up here. So let me hook this back up. Let's me go ahead and hook up the spring. Let me begin with the smaller of the weights. This is the 100. And as we worked out here in the derivation, I'll just kind of pull it down to there. And so now the spring has stretched what I called x naught or x0. And then, of course, if I were to pull it down a little bit more, that's the x1, and let it go, it would oscillate. And it would take a certain amount of time to do 1 cycle. And according to all this mathematics we worked out using our mechanics from Physics 121, and of course now extending beyond 121, we get this oscillatorial motion. That's what the equation tells us. And so after we look at that equation, we find the omega, and when we get that, we get the equation for the period. And it says it should follow that mathematical pattern. So we're going to see, does it follow that mathematical pattern? You can see that the period depends upon the mass. So we'll try different masses here. Okay? So I got my little stopwatch here. And I'll turn it on. Okay, and so when it gets down to the bottom, I will start it and then count to 10 and hit stop and write it down. So you can write it down. And so you need to write these down, and because eventually you're going to put them into graphical analysis and make a graph here. And like I said, step 2 is a lot like step 1. We're going to confirm to see if that equation is true. And then while in the process of doing that, we'll actually get the value of the spring constant. Okay, well, I've been talking for a while, so let me just kind of restart it, give it a little more amplitude here so I can kind of see it a little better. In fact, I'm going to kick the chair out of the way so I can kind of see it at its lowest point. And so you and I are lab partners. I'll be the one to record then the data here. So when it goes down, I'll go, well, let me get a little lower here. Getting ready, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so I got a value of 8 seconds, 0.70. And if I divide that by 10, that is 0.87. Okay, let me swap it out now for a 200. Now, of course, notice it pulls down the spring a little bit further, but as we said in the discussion here, as long as we're willing to measure x from the new equilibrium, this behavior for a vertical spring is just like the behavior of a horizontal spring. So I will pull it down a little bit and let it go. In fact, I can already see it's a little more sluggish. I can see in the formula that more mass would be a longer period, although it's got a square root, so it's not a nice linear relationship, but it does have more mass, more period. And so I'll just kind of do the same thing. I'll wait till it gets down to the bottom. Ready, and start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and so I got a time of 11.18, which when I divide by 10 is 1.118. And so there is the period for a mass of 200. Let's move on to a mass of 300. So I've got a 200 and a 100. I'll pull it down. I'll let it go. Again, you can kind of see it's already a little sluggish. Maybe I'll come down here, and when it gets down to the bottom, I'll hit start. Ready, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, and it looks like I got a 13.10, which when I divide by 10 is 1.310. Let's move on to the 400 grams, or the 0.4 kilograms. And so I'll put two 200s on here. And again, you can see it stretches it down. But again, if we're willing to measure from this new equilibrium, then it's just like a horizontal spring here. So let me pull this down a little bit, let it go. And maybe get a little bit lower. And say, okay, when it gets down, ready, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so I got a 15.14, divide by 10, 1.514. All right, now for the last one, I'll put another 100 on here. All right, so we got a 200, a 200, and a 100. So there's our 500 hanging from here. And I'll just let it go. Get the stopwatch. And down here, say ready, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, and so our last piece for step 2 is 16.64, which is 1.664. So you can see that the period's getting bigger and bigger. It's not even getting any bigger in a linear way, which is really good because you can see the square root in there. And so I'm kind of like this pattern. I hope it comes out well. But the truth is, I'm not going to plot this one this time. I'm going to have you plot that. So I, did you, whoa. So maybe I'll hold it up here in case you didn't get a good shot of these numbers. But, you know, pause the video here and you can then see those numbers. And those numbers, I want you to put in your graphical analysis. Okay? And you are then going to make this plot. Let's talk about this plot. In fact, let me take this down here again. We'll come back to it. But so you can see the board here. Let me come to the far side here of the board. And say, all right, let's make a plot. And I'm going to make a plot that's a little different than you might have thought. Let's read the question here. The question number 2, it says, determine the period of oscillation for the same masses you did in part 1. Okay, so we did that. And then from the appropriate graph, determine the spring constant. Now, your author's a little vague, from the appropriate graph, and he almost makes it sound like there's only one appropriate graph. You could get the spring constant in many, many ways, but let me show you kind of a fun way to do things. I think people's natural reaction is to plot period versus mass, because that's what we measured. But it's got a square root in it. And if you did that, it's not as convenient as what I want to show you. So if I were to plot period versus mass, and you can even give this a try if you want. Turn on your graphical analysis. You got to type in period. You got to type in mass anyways. And if you just plotted it, hopefully you would see something that looks maybe a little bit like a square root function. It's a curve. Curves aren't bad, but they're not best. Straight lines are easier to see the pattern than curves are. And so we like to say, if you could ever plot a straight line versus a curve, do the straight line. I like to put it this way. I have a simple set of axes, but a complex curve. Is it possible to make a complex axis with a simple curve? And in this case, it's actually very easy. Some of these are harder than others, but you'll see this a lot. It's a skill that you need to develop over these next 4 or 5 years that you're in college, because if you ever look at some advanced journals, some advanced data, you'll see the stuff that they plot, the axes that they plot are ridiculous. You look at the plot and it shows, like for those of you who had last semester in 122, one of our plots we did was the log of the tangent of the angle. Whoa. Does that even make any sense? Well, it's a complex axis, but it made a simple plot, and it was easier to interpret our data that way. And that's what I'm going to say here. Watch, I'm going to take that equation, the one that says period equals to 2 pi times the square root of k over m. And then I'm going to square both sides. So this becomes period squared. This becomes a 4 pi squared. This becomes then a k with an, sorry, got it backwards. That's an m over a k. It's an m over a k. But now I don't have a square root anymore. And if you then were to plot the period squared on the vertical axis. So this is the y. And mass on the horizontal axis. So this is the x. Then you would get a straight line where the slope is 4 pi squared over k. And so this is what I was meaning by saying it's nice to sometimes make your axes more complex so your graph is simple. And here's what I mean by that. And when your author says the appropriate graph, he's trying to say, don't do this graph. This is not the appropriate graph. The appropriate graph is a graph that makes your data a straight line, so your axes have to be something more complex than just period and mass. Now, I wouldn't call this very complex, and so it's a good one to start the semester off because I didn't change the horizontal axis, it's still mass. All I've done with the vertical axis is square it. So what you need to type into graphical analysis is the first column needs to be your mass. Your second column needs to be your period. Those are your two to type in by default. That, remember, I was showing you in part 1. And then you make a new calculated column, like again, I was showing you in part 1, and make a new calculated column, which is the period squared. And so this will be your second graph. And like I said, let me not take time to actually call up graphical analysis. I think if you go back and look at what I showed you how to do a graph for part 1, you can do part 2 here. And so hopefully you will get something that looks like this. So your second page for you to turn in is going to be this second graph. And here's the important part. Somewhere, either on the graph itself, which means you probably have to print it and then write by hand and then scan it to turn it in, or just save this graph as a PDF. But when you do the curve fit is going to tell you what the slope is. But then you're asked to figure out the spring constant. And so what is the spring constant? And this is why I made a big deal in part 1. The slope is not always the spring constant. It's not always so simple to go from the slope of the graph to the thing you're trying to measure. In part 1, they were one and the same. And like I kept saying in part 1, you're probably looking at me like you're crazy. Why do I have to write down the spring constant and the slope? Aren't they one and the same? Yes, but are they this kind? No. Right? What is the slope? And so hopefully you can see that all of this garbage in front of the x variable is the slope. So the slope you will get from the graph, and you need to set that equal to 4 pi squared over k. So in order to get the spring constant, you have to actually get out your calculator. And take the 4 pi squared, divide it by the slope in order to get the spring constant. So this one's going to take a little more effort to figure out the spring constant. And so make sure you do both steps. You get a graph that's aligned with a slope, and then the second part is you get the spring constant. So just like we had those two parts for step 1, we also have those two parts here for step 2. We have a graph with a slope, and then also how do we get the spring constant? So I'm trying to help you here with the spring constant and how you would make the connection between the slope and the spring constant. Because I won't keep doing that as the semester goes along. I'll just say, hey, do a graph, make it a straight line. So you got to plot some weird things on the axes to get a straight line. And then once you get that straight line, get the slope, okay? And then the final step is use that slope to find something, which in this case is the spring constant. Okay? And so that's the lesson to be learned here in the lab. We collect the data and we then eventually find something out of it. And we prefer to find things that come from a straight line. All right, well, let's move on then to step number 3. Okay, now to do step number 3. Step number 3 is kind of an extension here of step number 2. So I'm going to leave this last equation here from step number 2. And even the data table there, I don't think I'll need to go too much further. Maybe I'll just draw a vertical line and say, okay, what is step number 3? So let me read step number 3, because step number 3 is something that it's kind of fun to do here in the lab that we do not do in the lecture. And it's a great introduction here. It says, look at step number 3. It says, the analysis for the spring assumed that the spring was massless. No, I probably shouldn't have erased it. But do you remember going through this free body diagram and doing all the forces? Do you remember we said that the force pulling it down was gravity? And it was just the mass I was hanging. Nowhere in this analysis did I say that the spring had any mass. Does it? Yes. So I would say that what we've done in class and what we've done so far here in the lab has been a little shortchanging reality. Now, fortunately, many engineering problems, such as, say, the suspension on a truck, the mass of the spring is so small compared to the mass of the truck and the load that's in the truck, that to say that the spring is massless is okay, because really it is of negligible mass compared to the whole situation. And that's true for many, many cases. It's not quite true in our case, because our spring here is not much mass, that's true, but we weren't really hanging much mass. And so the mass of the spring could actually come into play. And see, we in class, and so just know this, we in class have treated all of our springs as massless. And in class we will continue to do that this semester, but as your education continues, that will not be the case. And so I'm trying to point out what we're mostly doing this semester, but this lab is a really good one because we actually have some real data where we've measured a spring that does not have zero mass. It is not massless, and in fact it is not negligible. So it should show up in our data. Let me keep reading. This, of course, is not true. As I just said, the spring does have mass. And a certain fraction of the spring's mass should be taken into consideration. How much? So, the reason I like this one is, as I said, this is more of an advanced topic. It's something we don't do in the class and in the lecture. It's something you won't do till your next level of classes. So when you transfer from here and you take your mechanics over at UCSB, yes, you will then start doing these same type of problems, but you'll have to worry about the mass of the spring. And they'll be harder problems. Of course, they're more advanced. You're now upper division. And so this is kind of our teaser towards it, because I would say that this data right here, that is this data right here, and I don't know if you caught this. Did you notice when I drew this straight line, it did not go through the origin? It was a little above the origin. And if you look at this equation, y equals slope times x, this equation says it should go through the origin. So here's what I'm claiming. I'm claiming that my real data, the real data I took, this stuff right here, the stuff we just did in step 2. So here's the neat thing about step 3. Step 3, we don't have to make a new graph. Okay? We're going to use the graph we just did in step 2. And now we're going to look a little closer at it. And when you look closely at the data in step 2, you will see that your graph does not go through the origin as the theory predicts. And I'm trying to say, is the reason the theory predicts it goes through the origin is the theory is off a little bit because the theory says our spring has no mass, and that's not true. Now, it's not far from the origin. So that also justifies our discussion in class that, okay, our springs do have mass, but they're usually pretty small and negligible. Okay, totally agree with that. So in class and on tests, we're going to say, treat the spring as if it has negligible amount of mass. And that's totally true, okay? But as long as we got some data, this is, I really, really like step 3 here. Step 3 is a little more advanced. Step 3 is like, whoa, wait a minute. The spring does have mass. But the theory of a massless spring says it goes through the origin, and this one does not. Can I use the fact that it doesn't go through the origin to figure out how to deal with a spring that has mass? And the answer is yes. So let's do this. Let's come over here and rethink about the experiment we just did in step 2. And you see this mass? That we have this 0.1, 0.2, 0.3. I claim that that number, that mass, is not really the total mass. That's the mass that I added to the spring. That would be the total mass if the spring was massless, but it's not. So I'm going to do this. I'm going to say that a better analysis is to say that the total mass is actually to the mass, what I called M, the mass that I'm actually hanging, plus the spring. The whole spring? Well, let me reach over here and grab this spring, because this is where it gets even funner. If this spring is hanging and we put on our loads and it goes up and down, you can see that this part of the spring seems to move more than this part of the spring. Because maybe your first reaction would just say the total mass, and this is how your author writes it, is the mass you're hanging plus the mass of the spring. But then as you look closer at the spring, you realize that part of the spring up here is not moving. Part of it down here is moving the full amount. The stuff in the middle is only moving a partial amount. So your author says, if you were to add all the mass, that would probably be a mistake. And so just like adding none of the mass of the spring is a mistake, adding all of the mass of the spring is also a mistake. Oh, so maybe it should be half as much. Well, maybe. And here's the beauty. The data, we have data that we can look at. We have data we can study. We have data that we can tell us, okay, what amount of the spring should be considered as added to the mass that we're hanging. So your author does this way. Let's call it F. F is for fraction. F is then a number that would be greater than 0 but less than 1. Let's look at our data closely and see if we can find out what F is. Because I hope by this point in the conversation you will realize that F should not be a 0 or a 1. It shouldn't be the whole mass of the spring, and it shouldn't be none of the mass of the spring. It might be half. By the way, it's not. So what is it? And I claim, I'll keep saying it, you have data that shows what it should be. So let's find it. And so step 3 here, I'm not going to collect any more data. I'm going to use the data that I already did in step 2 and find this value of F. And how are we going to do that? Well, that's why I left this equation here. Because if I had gone through that analysis and considered the mass of the spring with this formula, it would have been m plus a fraction of the mass of the spring. And so then when I squared it, I would get period squared is equal to 4 pi squared over k times m plus f times the mass of the spring. And then, keep working on my math, if I do the distributive property, it would be 4 pi squared over k times m plus 4 pi squared over k times f times the mass of the spring. And when I make a plot that has period squared on the vertical axis, so if I think of this as the y, and I plot mass on the horizontal axis, so I think of this as the x, and see, and that's what I did plot, right? This is what I did actually plot in step 2. This right here would be the slope, and this right here would be the y-intercept. I'm hoping you're beginning to see it. If you don't see it, let me explain, because this is why I like this step of the lab. See, this one is saying that, and I'll go all the way back to step 2. In step 2, when we ignored the mass of the spring, we got an equation that just said y equals slope times x. There was no intercept. But when we reanalyze it here in step 3, and we consider a fraction of the mass of the spring, we see that our plot should be a line with an intercept. And that's why I said, back here in step 2, that you will have a small intercept. And it'll be so small you might not even have noticed it. You're just working along saying, oh, fine, fine, fine. But I claim that that intercept, the y-intercept, is caused because of the fact that the real spring that we're using doesn't have mass. And this will give us an opportunity then to find this value. So here's the third piece that you're going to turn in for the lab. Find f. How do you get that? Well, remember, you've already done this graph. And when you did this graph, the computer gave you the slope, which we use the slope to find the spring constant. But the computer will also give you the y-intercept. And so I claim that this right here, the y-intercept, which I will call b, equals 4 pi squared times f times the mass of the spring over the spring constant. So you just did the spring constant back in step 2, so use that spring constant. Use your graph to get the y-intercept. And I will measure the mass of the spring right now for you. And so you know everything in this equation except for this magical number I'm trying to discuss. When you are working with a real spring that has mass, you have to think about not just the mass that you are hooking up to the spring, but then a fraction of the mass of the spring itself. Like I said, this is more of an advanced discussion, which is why we're not going to even have this discussion in class, but we are going to use the data to prove what that number is. And so I want you to find that number. And of course, for you to find that number, I have to now give you the mass of the spring. So let me come over here to our scale, which haven't turned on our scale yet, this semester here. So let me plug it back in and let me give it a chance to boot here. There it goes. And let me put it on the scale. And we are looking at points. So mass of the spring, 0.158, 7? Yeah, kilograms. And so let me say it again, your job here in step 3 is to find this fun number, find this fraction, okay? You get the b from your graph, you get the slope, the spring constant from your graph, which is from the slope. And now I've just given you the mass of your spring, find F. And as I said earlier, it's not 1, it's not the full mass of the spring. It's not 0, it's not no mass of the spring. It's not even 1/2, it's not half the mass of the spring. But what is it? You tell me. That's your step. Okay, so finally, step 4. All right, let's do step 4 here together, and then this will be the 4th thing that you put all together. You make a PDF and you upload it to Canvas before next Sunday night. Okay, so what is step number 4? And you'll probably be glad to hear, now that I've talked so long here, that step number 4 is actually the easiest of these 4 steps. Step number 4 is here because if you come back to our derivation in step 2 here that we did for a dynamic spring, and like we did in chapter 15, you'll see that the period depends upon the mass and the spring constant. There is no amplitude in this equation. In other words, if I took a spring, and so here's the spring hanging down, and I put a mass on it, and then I do a second time, so let me put a mass a second time. Oh, let me make it the same mass, so it stretches the spring the same amount. And if I pull this down, say 2 centimeters, 2 centimeters, so that's its amplitude, and I pull this one down 4 centimeters, they have different amplitudes. Does that affect the period? I mean, you might stand back and look at this and say, well, yeah, you see this one has to travel further. This has to go down 4, back up 4, then it goes up 4 more, then it goes back. And so this is moving in one full cycle. It would go, I guess, up 4, down 4, down 4, up 4. So 4 times 4, that's 16. This would go 16 centimeters, where this one would go 2, 2, 2, 2. So 2 times 4 is 8. So this one would move 8. This one moves 16. The one with the bigger amplitude has to move much further. So maybe that should take longer. Well, look at the equation. The equation doesn't have anything in here that says amplitude. There's no A in here. So if you change the amplitude according to this equation, you should still have the same period. Wow. But it moves further. Yes. But as I hook it up, hopefully you will also see it moves faster. And so this one here that moves further also moves faster. And the time it takes is the same as this one. So small amplitude ones move slower, big amplitude ones move faster. They end up taking the same amount of time, and it's kind of a neat experiment, that's why I want to do it, to actually see that the period it takes is exactly the same regardless of what its amplitude is. So, your table, and you're not even asked to do a graph because it's so obvious. At least I hope it is. Let me collect the data and see if it is truly obvious. But your data in step number 4 is to do this. In the first column, you are to change the amplitude, and I'll just do amplitude in centimeters this time. I'll use the unit of centimeters. Because you're asked to pull it down just a little bit too. then a 4, then a 6, and then an 8. And then, of course, you're asked to measure the period in seconds. And just so we can get a little more accurate data, we will measure 10 oscillations like we did in step 2 and 3, and hopefully get the same period. Oh, within reason. Remember, your partner here keeps making a few mistakes. So hopefully all of these numbers here are pretty close, even though the amplitude has changed by a factor of 4. Okay, and so this one here travels 4 times more than that one, and yet the greater distance will still end up with about the same period. So our last step here for today is to come over here and make some more measurements. And so our data table is going to look like this. We're going to have amplitude in centimeters. And you're just going to have to write down the data here and turn that in. You don't need to do a graph. You'll see, because it's just all the same numbers. There's no point in doing a graph. You're going to see the same numbers and go, oh, yeah, they're the same numbers. Why do a graph? Okay, but I'll put down 10 periods in seconds and then eventually divide that by 10 to get 1. So 2, 4, 6, and 8 is what we're asked to do here. All right, so let's mount it back up. I think the spring is still over here on the scale. And so let's clamp this up. The amount of mass really doesn't matter because we're not going to change it. So the author just says, you know, pick a mass of your choosing. I'll just kind of pick the middle and go with the 300. Okay. So I'll put a 300 on here. And so I can have something to kind of measure. I'll just say, okay, the bottom here is about at this 7. So if I pull it down to a 9 and let it go, and quickly come over here and turn on my stopwatch, let it go down, ready, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I get a time total of 13.34, which when I divide by 10 is 1.334. Okay. Now, I'm giving it a little bigger amplitude, so pulling it down 4 and letting it go. Resetting the stopwatch. Okay, ready, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I hit it with my finger, but I barely. Oh, good. And I got a good number, 13.28, which is 1.328. And other than a little human error there in my reaction time and maybe even my finger bumping it, you'll see I got the same period. All right? So let's try the next value, which is an amplitude of 6. So 1, 2, 3, 1, 2, 3. Okay, so there's a 6. Let it go. And then I can say, okay, ready, get, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and then I got a 13.10, which when I divide by 10 is 1.310. So again, they're pretty darn close. At least they're all the same within a tenth, and then the hundredths are off just a little bit. And again, that's probably me messing with it. Possibly I'm seeing a little more air friction, but I don't know if I can actually measure anything quite that accurate. But maybe I am, because I would expect to see that way back in the hundredths of a second. I would expect more air friction if it is moving faster, which then would lower the period. Okay, so now we got to go to 8. So 1, 2, 3, 4, 1, 2, 3, 4. Okay, and let it go. And our last one here, to wrap it up here for our first video lab for the semester. Ready, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, and I get a 13.16, which when I divide by 10 is 1.316. And that is, as I said, illustrating exactly what you want. So just type in those numbers into a chart. That's going to be your last of your information to turn in. Well, I shouldn't say last, because there's 2 questions, and I'll deal with those in a second. But that's the last of the data and analyzing the data. And hopefully proves the point here that the period is independent of the amplitude. All right, well, 2 last things to do is at the end of each lab, you will have some discussion questions that you need to answer. Usually the point of the discussion questions are really good, and the way they are worded sometimes is questionable, and I would say that is true in this case. Let me clear off a little space here and let me help you with them. The first one, I don't think you really need any help with. I already answered it. I'll just read it. It says, question number 1, explain why the intercept in part 3 will yield the fractional mass of the spring. And so you heard me talk for a long time about how the intercept was not 0, how it was off. And that was good. That showed that the spring actually had some real mass, and it was that intercept that was leading to it. So I think you can answer that one. And you don't need to be real clever with your words. I just want you to put in enough words that I know you comprehended what I was explaining. But number 2 is actually a really good question, but he has not given you the tools and the resources to answer it, so I want to do that now. Number 2 says, if you were unaware of the relationship between the period and the mass, what graphing techniques might you utilize? And he's really getting at something really deep that I want you to see and understand. We're actually going to use in the second lab, and then a bunch more labs as we go along this semester. But the reason I say he hasn't given you the tools at this point is because we did the easy one. Let me come over here and show you. Remember I said that one of the great techniques of doing graphs is to take something that has a simple set of axes but a complex plot and change it to a complex set of axes with a simple plot. Straight lines being the simplest of the simple plots I can think of. And we were able to do that because we already knew the equation, and we knew that a square root was curved, and if we got rid of the square root, of course by squaring we would get rid of the curve, so that's why I squared it. But I could only do that because I knew the relationship between the period and the mass. I knew what to do. All right. And the world doesn't always work out so well that you already know the relationship. But I would say it would be better that way. If you already knew the relationship, you could study the equation, and once you study the equation, you can decide, okay, what do I want to plot on my axes? What are the complex axes I want to make in order to make a simple graph? But he's trying to say is sometimes we don't know what the equation is. In fact, that's the whole point of doing the experiment. Maybe you put a new model of an airplane into a wind tunnel, or a new shape of a car into a wind tunnel, and you don't really have an equation. You just measure the air speed and the friction, and then you just have those pieces of data and you plot them. And there's a lot of fancy techniques. So his question is a little too general because it says, what graphing techniques could we utilize? Well, there's a lot. And I want to show you one special one. And I think this is what he's after because he uses it in the next 2 labs. And then we use it a bunch more throughout the semester. And it looks like this. Let's just say that I had a mathematical graph, y versus x. And maybe I have something that looks like this. It has an amplitude, it has x, and it's raised to some power n. I think you already know that if n equals 1, you get this shape, right? So there's n equal 1. You get a straight line, or more appropriately, a proportional graph. If n were to equal something less than 1, n less than 1, it would curve downward, like a square root function. Oh, should I take the thing down again here? So, what about n greater than 1? And then I think you know, like n equal to 2, a parabola would curve the other way. I'll just say greater than 1. And so what he's trying to get at in here is that since you don't know the equation between the y and the x, so I'll say it again, here we actually knew the equation. So by knowing the equation, I knew what to do. I knew to take the square of it. But, you know, if had this been a cube root, I would have known to take the cube. But if I don't know what it is, what do I do? And it was Newton who brought this up first. He said, as long as it's raised to any power, watch this. What if you take the log of both sides? And so on the left-hand side of the equation, let me just log it, leave it alone and leave it as log y. But the nice property of logarithms, and I'm going to use 2 properties of logarithms. The first one is to say if you have a product, you can break that apart into a sum. And the second nice property of logarithms, called the log roll, is to take the exponent and roll it down the log so it becomes a coefficient in front. And if you study this really carefully, and you make a plot so that the horizontal axis is not x, but is the log of x, and the vertical axis is not y, but it is the log of y, you will see that this is the equation of a line, isn't it? No matter what the value of n is. Where you will get a line and the slope is equal to n, and the y-intercept is the log of a. And so what he's trying to get at here is if you ever come across a graph that is not a straight line, and you don't know the equation to figure out what to plot on the horizontal and vertical axis, The thing you should do first is plot the log of x versus the log of y. Because anything that has this form, so I'm not saying every graph you do will come out to be a straight line, but I'm saying that any data that follows a power function would then come out to be a straight line. And once you get that straight line, if you measure its slope, you now know what power it's raised to. And if you measure its intercept, you now know what the coefficient of the constant is in front of the power function. You can get the equation. And so the technique that he's after here is you first always plot x and y. The second thing you plot is the log of x and the log of y. Because if you get a straight line, you know it's a power function, and you know what the power is by the slope, and you know what the coefficient is from the intercept. And I picked air friction, you know, as I said, you put a test vehicle in a wind tunnel, because those tend to be power functions. And so the engineers just take the new car, they throw it in, you know, they design it, usually designed out of a clay or a wood mold, and they put it in the wind tunnel, and they just blow the air, and they just collect data. Hey, at 5 miles an hour, this is the friction. At 10 miles an hour, this is the friction. At 15 miles an hour, this is the friction. And they just go through a whole range of wind speeds from 0 to 100. They get the data, they put it in a graph, and it's not a straight line, and then they plot the log of it, and they usually get, for those kind of things, straight lines. And then they look at the slope, they look at the intercept, and now they have the equation between speed and friction. They didn't have to analyze and do a whole lot of physics and mathematics behind it. They just took data. They did an engineering approach instead of a science approach, and they got the information they need in order to design the car and to put that data into the computer and let the computer kind of analyze the gas mileage and all that good stuff here. So that's what it's after. So I hope I didn't take too long on number 2, but I wanted you to see log-log plots, because we're going to do a lot of log-log plots. And anytime you don't know the relationship, or even if you do know the relationship and it's a power function, because that's what's going to happen with us, we're not going to be doing something new. We're going to know the relationship, but we're going to do the log-log plots just to convince ourselves that power functions always come out to be nice straight lines. And when you do the power function, you can look at the slope and find out what it's what the power is. So keep that in mind for next week's lab, because we're going to do a log-log plot. All right, I better call it quits here. I've been talking a long time, and like I said, do parts 1 through 4, answer these 2 discussion questions, and turn that in, and I'll see you later. Bye now.